is Griffiths E&M example 6.2. So in example 6.2, we are told that we have a long copper rod. So it's made out of copper. It carries a uniformly distributed current that's going upwards. And we are told to find the auxiliary current, the auxiliary field, H, everywhere. Okay. So it's useful probably to figure out, what direction some of these fields are pointing, because we have a lot of things going on here. Okay, so I have I pointed up. Well, I know that that tells me that that my magnetic field must be pointed along the azimuth, and according to the right-hand rule, this gives me B. Okay, so B is pointed like this. All right, I can go ahead and look on table 6.1, which is in section 6.4, and that tells me that that copper is slightly diamagnetic, meaning that the dipole moments are going to point in the opposite direction of the field, and therefore the magnetic moments of that material are going to be pointed in the opposite direction. Okay, and then my goal is to find H. This looks like a problem we've done before, so I'm going to go ahead and take the dot of this around a path is equal to I times free enclosed. Well, if I'm going to enclose some current through a path, that means I'm going to go ahead and draw a loop that looks like this, and that means that using the right-hand rule, I is going up, means that H must be pointed along this direction. There we go. Okay, so I can go ahead and do this for outside. I get H 2 pi S is equal to I. Right, so that's all of it. Then H is equal to I over 2 pi S phi hat. That's for outside, and then go inside. This I is uniformly distributed, so I can go ahead and say that whatever amount of current is captured there is a fraction of the total. So that's I pi S squared over R squared, and that means H is equal to 1 over 2 pi R squared S phi hat. There we go. So we can also ask, what's the magnetic field? Okay. Well, I know that I can go ahead and write the magnetic field as being related to H and M. That is mu naught H plus M. And I know that outside of my cylinder, my magnetic field is 0. So therefore, my magnetic field is mu naught I over 2 pi S in the phi hat, which is exactly what it was before, for previous chapters. Now, if I wanted to go ahead and figure out what the magnetic field was for the inside, I would take mu naught H plus M I believe that's probably still mu naught. And I would need to know what H is inside. Well, I do. I know what that is, but I haven't actually figured out what the magnetization looks like inside of that field, so I can't actually give you an answer for what B looks like. Okay, but H is useful in calculating the magnetic field.